variables, right? So we've been working extensively with numerical variables. But if I asked you to tell me whether males or females are more likely to have gotten a flu vaccine in New York City this year, well, you got a categorical and a categorical. You could find the proportions, but you really don't have tools to deal with categorical variables. Numerical variables, we've done tons of stuff. Now we're getting into other kinds of variables, categorical variables. One of these sources, one of the major sources for data sets for the project, if you want to do them, is the New York City Community Health Survey. And in that community health survey, there are some numerical variables. They ask people there, they ask 8,000 people in New York City using a phone interview. They ask people something like 150 questions. How they get them to stay on for 150 questions, I have no clue. I don't know if I honestly don't know if they pay them, if there's some inducement. I don't know if in the environmental class, I mentioned this to some people. I do a lot of stuff in water testing during my day job. And you know the story, the shoemaker's kids always have the worst shoes, right? Because the last thing he wants to do is work on his kid's shoes. So I have a lead main coming into my house. I had my lead main come into my house since it was built 85 years ago or something like that. So I get a sample bottle from the Department of Health every 6 months to take a sample because they're required by EPA to test the point of use. Because a lot of the copper, solid copper, lead mains, they're part of the house system, not the street. So the EPA wants to make sure that they're not just testing the supply where there's never any lead, right? It always winds up coming from the building piping. So they send me a sample every 6 months. They follow the instructions, either first draw or after a certain number of minutes. I send it back to them. They give me $100 off my bill every year for doing that, right? Which is a nice deal, right? One of these days I'll get around to replacing the main, and there goes my $100 credit. But in the meantime, maybe I won't tell them. That's not ethical. But at any rate, in the meantime, that's what happens. So I don't know how they got people to sit down on a phone for this period of time to answer these, and a lot of them pretty personal questions. But they did. So they have 8,000 people. They do it every year. So you can get this data set every year. There's a few of these variables. They ask them about age. They ask them about, I guess they might ask them about weight and height and stuff like that. Some other general stuff. They do some calculations like BMI. So there might be 5 or 10 numerical variables there, but most of the 150 are categorical variables. Do you have health insurance? What kind of health insurance do you have? Have you gotten a flu shot in the last 12 months? Has anyone told you you have asthma in the last 12 months? Has anyone told you you're diabetic? A physician told you you're diabetic in the last 12 months, etc. So that's a lot of those yeses and nos or categories of various kinds. So since that's the nature of the data set, I want to get you started in understanding a little bit about evaluating categorical data, and I'll talk to you about like what the option is with doing a project or doing the exam. I do grade the projects pretty liberally, so just so you know that. Okay, now, but on the other hand, I ask you to do basically the project consists. Well, as a matter of fact, I'll open it right now, so that you have this practice stuff. As far as the exams are concerned, I moved it up a week so that I could just cover in the exam the stuff we've done up to now, right? So anything going forward is not, and chi-square analysis variance not going to be on this exam. I think that'll make it better for you because once we start throwing in this other stuff, it's kind of like a curveball because they really are different tests. Now, if anyone has a real legitimate problem that, gee, I scheduled vacation for that day, I'm having surgery, I'm being inducted into the military, whatever might happen. If you have a real problem, just let me know and I will try to accommodate it, okay? So I understand it's an inconvenience and it's a worry. It's like instead of being how it is. Instead of being further away, it's closer. So it just seems more terrifying, right? So and which the last thing it should seem is terrifying. So if anybody has a real problem with it, just let me know and I'll make some sort of accommodation for you. Okay, even if that's just you're just so nervous about it that you really need the extra time, I'll figure something out. Okay. So I apologize for that, but I really think it'll work out better for everybody this way, for almost everybody this way. So at any rate, so project, let's talk about the project. I put some instructions here on the project, and basically the project consists of consists of basically what is a presentation that's called a poster. Now, if any of you guys have gone to, I could put up some pictures of actual, poster sessions at the American Public Health Association, other organizations like that. But you go to these annual conferences or semi-annual conferences, and they will have many speakers. You could have dozens of speakers talking about their research, latest stuff in latest developments in their field, and so on and so forth. But that's dozens. They literally have hundreds of people within an organization like American Public Health Association that are doing work and research and publishing, right? So there isn't an opportunity for them to communicate all that. So what they do instead is they have poster sessions, and these poster sessions consist of you remember when you did a science project in elementary school, you got a big piece of O-tag and you put stuff all over it, stuff like that. It's kind of like that, except on a professional level. And they will, on a large poster, like maybe something like 4 by 6 foot, they will put their name of their paper, their objectives, their research, some background, what data they've collected. They'll summarize it, have charts or data. They'll summarize what their results were, and they'll give you some sort of conclusion. So literally, they'll have halls where there could be hundreds of these posters in aisles, and you walk up and down the aisle, and let's say you're interested, like I'm interested in Legionnaire's disease, right? And there's a lot of people right now doing a lot of research on Legionnaire's disease. To walk up these aisles and this guy's doing some stuff on a pandemic flu, and this person's doing some stuff on Ebola, and this one's, I keep walking down, very interesting, very interesting. And then bing, I'll see somebody who's doing some research on Legionella, and I'll stand there and I'll read that poster. And very often they'll be standing there. If you have questions for them, you can interact with them and stuff like that. So you guys are going to make a poster, right? You're going to decide, well, one of the options here is to look at, getting into flu season. So one of the options here is to examine who and why people get flu vaccines. You can look at it in terms of whether gender influences whether a person gets flu vaccine, whether ethnicity has an influence on it, whether a person has a primary care physician, yes or no, has, and so on and so forth. So you can look at it from a number of different angles. So what do you do? If you look in here, let's see, option A, there's a description. Okay. And the description says, okay, what do you got to do? Well, it's going to be 5 to 7 pages, right? But keep in mind, we're making a poster. It's not something somebody's going to sit down with a magnifying glass and read. They're going to be standing a couple of feet away, right? So make the font, like for instance, the header is maybe 18 point or 24 point. Most of the text in there, 14 or 16. So you could stand a couple of feet away and be able to read it. So when I say 7 pages, you're doing a lot. You're condensing a lot of information into that 7 pages. You're trying to be concise. Okay, so what's going to be in there? It's going to be an introduction. What's the problem? Why are you doing this? What are you interested in? Descriptive statistics. Okay, you're looking at gender and flu shots. Well, what in this population? What's the ratio of males to females? And so on and so forth. Or if you're doing ethnicity, what different groups are represented? What are the ethnic groups? You might have a chart that describes them. You might, if there's something relevant that you want to also bring up, like maybe women are a lot less likely to have health insurance than men are. You might want to put that into your descriptive statistics also, right? So you want to cover your descriptive statistics. What's the data like? Then you might want to discuss your methods. In other words, how are you going to attack this problem? If it's a numerical variable, you might say, well, I have a null hypothesis, and I'm going to use a t-test, an independent samples t-test, and so on and so forth. And then you would actually go ahead and do that, show us your results for that analysis, whatever it was, chi-square, odds ratio, whatever it was, show us your results, and then discuss it and give us your conclusion on the paper. Right? So not really, you got to be pretty concise. So you're not going to be doing a ton of typing. So I might include in the introduction, you should research the topic a little bit. Like in other words, do a search here or there where you have access to all sorts of databases. And so did they still do a thing in the library when you first come here, where they spend a couple of hours with you and tell you about all the online databases you have, Medline, and they still do that. So you got all sorts of places where you can get information. So just do a little bit of quick research on it, on whether somebody has done some work on gender and vaccines and health insurance. Yes. No, one like one, two, three, whatever looks interesting. If one interesting paper that relates to what you're doing, right, is better than 20 that like are just scattershot. Okay, so one or two would be nice, just so that I know you've done a little. You've gone online and you said you've gone something. I don't mean like Google, like the New York Post, right? So I mean, something that would be like kind of a legitimate, health information source. So what's that? Well, we're going to discuss that in a second, right? So at any rate, so now here's the rub. We're doing a poster. What did I just tell you? You look at the poster. Oh, that looks interesting. Where is that person? Right? I'm going to ask you to do a 5-minute presentation here. So we get poster board. We've done this before. It's fun. We get poster board. You get you 7 pages. You poke them up there as if it, rather than get something printed professionally. You just we just use what do you call it? Push pins or tape or something. Put it up on the poster board, and you stand in front of it and you give a presentation. Right. So if we get half the class that's interested in doing that, it'll be pretty interesting. We'll have hear some very interesting stuff. Right. So I would prefer you do the presentation. If you got like real stage fright, let me know. We'll get around it. Right. But I mean, that's really part of the deal here is that I want you to feel comfortable. Number one, looking at data, saying to yourself, how do I interpret this data? What test do I use for this data? How do I describe this population with descriptive statistics? What test should I apply here? How do I do it? And we're not talking about 20 tests. We're just talking about one statistical analysis, right? So how do I do it? And now how do I describe what my results are? Yes? And instead of Microsoft pages that type, could we do like PowerPoint? Yes. Oh, yeah. In fact, I think I mentioned that. I think I mentioned that in here somewhere that you could either do this in Word or I like using PowerPoint because PowerPoint's a lot easier to move graphs and tables around. Yeah, absolutely, positively. If you do a PowerPoint, can you project? It'd be easier if you print it out, I think, because otherwise we're going to get into using trying to get everybody projected on here. If I can set up 4 or 5 of these poster boards, so as one person is presenting, the other 3 or 4 people can set up. So it'll go. We've done it before. It'll really go quickly. Yes. And for the graphs and tables, you would take that from the research that you're reading. You could do. I'm sorry. Say it again. The graphs and tables, you would take that from the research that you're reading. No, you're going to make those. In other words, the graphs and tables are tables of your stuff. Like in other words, like a pie chart or a bar chart shows the relative number of people that had insurance that got a vaccine versus didn't have insurance or something like that, or descriptive statistics, the proportion of the population that took a males and females that had a vaccine that were vaccinated and so on. So that would be your charts, right? Okay. And you don't have to use SPSS. You can, if you want, use SPSS, because a lot of the data, I'm going to give you the data formatted for SPSS because we're talking about 8,000 people, right? It's big data sets. So you're not going to want to work with that in Excel. So you can use the charts you can produce in SPSS, or you can summarize those and use PowerPoint or Excel or something like that, or whatever program you want to make charts. In fact, you can make nicer charts, I think, in Excel than you can in SPSS whatever you feel comfortable with, really. This is not a PowerPoint or Word or whatever course. It's biostatistics course, but I want you guys to get some feel for doing this so you're comfortable with it, not just comfortable sitting there taking a test, and then if you ever have to apply it, hey, I don't know what to do, and we just took tests. I know how to take the test, but So I mean that's the point of this whole thing. Okay, so you have that choice, and I'm giving you, so for option 1, I'm giving you a data set. I'm giving you the fields in the data set that were in the community health survey that have something to do with influenza. Part 2, you could do any other variables that you want in the community health survey. I'll show you what that looks like shortly. You could either use the one I gave you, what I'm giving you where I've reduced it to, well, I will reduce it to just several variables like this, and you can choose from them. Or you can take the whole community health survey and choose whatever variables you want. So if you're in nutrition, they have lots of stuff on nutrition, how much fruit people eat, how much exercise they get, how many sugary drinks they drink, and so on and so forth. They have all sorts of stuff in there. They have stuff on exercise. You'll see as we go through this, you'll see as we get into it, you'll see how the breadth of that. And option number, so you could do what that one data set if you feel most comfortable with me just giving it to you. Number two, you could choose other variables in there that you might be interested in. And number three, if you're doing any work in another course, or if you're doing something at work and you have some sort of data that you have permission to share, like is not like HIPAA protected or something like that, that you want to use as a data set and do an analysis, it's perfectly fine if you do that. The only thing is, the thing I would ask you is that I'm going to give you, after the test, maybe another week, if you plan on using a different data set than the option one, I think it would be best if you communicate to me, say via email or something like that, or maybe I'll make somewhere where you can upload it. What variables you plan on using other than that, and what kind of tests you plan on applying, so you don't wind up going off on a tangent and wasting a lot of time. And also if you're planning on using some other data set, what you plan on applying, just so I can get a quick look at it, and make sure that there are no real, you don't wind up painting yourself into a corner, as they say. Okay, so but it's got to be more interesting than taking a test, right? Okay, but like I said, if you're not comfortable with I can give you a test. There will be a test for sure. There'll be a test available, and it'll cover chi-square, analysis of variance, and regression, the last three topics here. Okay, chi-square is going to be interesting to us, especially now, because I know there's a lot of application to this particular data set. Okay, so that's the project. Okay, and the due date for it is the last day of the class, which I think is December 18th. Am I correct about that? Okay, we're all in agreement. It's December 18th, that Monday. December 18th is the last day.
So if you take the final and then cover chi-square.
Chi-square, analysis of variance, and correlation and regression. Those are the last three topics in the course. Okay, chi-square is chi-square, including this thing called odds ratio and relative risk, which we're going to get into. That is related to categorical variables. Analysis of variance, believe it or not, analysis of variance, despite the way it sounds, is another way to compare means. When we do the t-test, you only can compare two means, group A against group B. Analysis of variance is a situation where you can compare more than two means at the same time. Like, let's say you wanted to find the average BMI. You want to compare the average BMI for people living in the 5 boroughs, Brooklyn, Queens. So you got 5 BMIs you want to compare, 5 samples, right? You can use analysis of variance to do that all at once, rather than using a t-test where you would have to compare Brooklyn and Bronx, and then Bronx and Queens and Brooklyn. You'd have to do it many times, right? It's a bad thing all by itself. Yes.
I had a question in terms of the project. So then do we only narrow it to using 2 variables?
You can use 2 or 3. You can use. I'm encouraging you to stay focused, like not go nuts, right? But yeah, if you want to use 2 or 3, you want to examine 2 or 3 of variables, but don't examine flu vaccine versus every possible amount of fruit people eat and how much exercise they get. Don't go nuts. Yeah, okay. Just keep in mind this is something you want to be able to communicate with us in 5 minutes, right? Okay.
And also, I think the last day of class is on December 12th.
Yeah, but I think the finals week is the following. Yes, the 18th would be finals week. Okay.
So we would have to come in 35 minutes.
Yeah, for that Monday, just that one day. Yeah, that one day. And you want to know something? If there's an issue with that, like you're taking off for Portugal for the summer, for the winter, or something like that, take me with you, number one. And barring that, let me know, and maybe we can do some of the presentations on the previous week. Okay? All right, let's move on from there. Okay, so anyway, well, let me show you what the data looks like.
Can you just go over what's the last day of class?
The last day of class is the 12th. The 18th, excuse me, is it the 12th or the
Well, it's on
11th?
Tuesday, but
The
it's
11th. Yeah. Last day of class is the 11th, and finals week starts that right after that.
So we have to come in.
Yeah, we're going to do the presentations and the exam on the 18th. Or if you're really desperate to get out of town, we can arrange something where you can do a presentation the week before. Okay, that might be easier too if we get a lot of people doing presentations. It's kind of, it can get a little hectic.
We'll take it to Portugal.
Okay, I've never been to Portugal. I really want to go. But at any rate, yes.
One more question. So it's an actual poster board, right?
Oh, well, you're going to be printing it out, right? And then we're going to have push pins, so you can mount it on there. Yeah, I can come up with pictures from previous semesters. No, I'll supply the poster board. You just print it out on the 7 pages so you can put them up. Right.
I gotta go get it. Where you get a poster board?
I was thinking. Didn't you do science projects when you were in elementary school? Huh? Right, volcano. Didn't you build a volcano?
We just have it projected on our PowerPoint. We have it projected on the screen.
Well, yeah, that gets. There's only one screen and one computer. When we do this with the boards, it does two things. It kind of emulates what you would do with a real poster, right? With people listening to you discussing it. And it also things move a little bit more smoothly because if I got 5 of them set up, when one person's finished, they can take their stuff down, and the next person can put it, so we can go around and
Okay, so you're bringing
keep
the
it moving.
board and we bring
Yes.
our 7-page paper.
I'll take care of the poster boards and the push
With the
pins.
thumbtacks.
Yes, I'll bring everything except you bring your presentation. That's
So
it.
are we gonna?
What's that?
No, I'm kidding.
Oh, listen,
I'm
we
kidding.
have done that. We have done that.
Bringing coffee and
Yeah,
donuts.
something like that.
Oh yeah.
Although this is a nutrition class. I have been criticized for bringing in donuts to nutrition majors. So don't think that has
They're
it.
gonna bring out the stack.
Yeah. Yeah, in moderation.
So we are going to submit the 7 pages to you
Yeah.
when we're done.
Yeah. Oh, yeah. Oh, by the way, guys, part of this is that in addition to the presentation, you will upload them. Your presentations.
Okay.
Okay. So I just want to show you what the data set looks like. Oops. Cancel.
Professor,
Yes.
can we do one of these practice problems?
Oh, sure. Hang on. Let me get started on some other stuff. We'll get to that. Okay. What's that? I'm sorry, to review all day? You mean like when? Today? I could do that. I just want to introduch chi-square. Let me go through this. I just want to go quickly over, just introduce chi-square and odds ratio and relative risk. And then I'll spend the rest of the time doing a review session. Okay?
So let's see an example of the.
Okay, hang on a sec. Let me just go through this so that I can show you what this looks like. Okay, so if you look up behind me, this is on Blackboard now. You can get this on Blackboard now if you want. This is a code book. This describes all of the variables that were in this community health survey. There's actually another document that actually shows the actual questions that they asked. Like for instance, this first one of the first ones that come up. Do you have any kind of health insurance, including private insurance, so on and so forth? And how is it coded? 1 is yes, 2 is no, right? The others we can ignore. Don't know or refuse, we can ignore. Okay, so it's got insurance questions on it. It's got questions about asthma. Let me see if I can't find asthma questions. Okay. Here we go. Have you ever been told by a doctor, nurse, or other healthcare professional that you have asthma? 1 is yes, 2 is no. Categorical variable. Last thought, have you had an episode of asthma attack? Yes or no, and so on. How about let me hit done here, and let me go back and try sugary. How about sugary drinks? I wonder if I can find that. Nope, sugar, but sugar. When ounces of sugar sweetened soda per day that you drink, and there's categories: this to that, or more than that, more than 32 ounces, and so on. They give it in categories rather than in actual numerical variables. How often do you drink sweetened drinks? 0 to 23 per month, whatever that is. But you'll see that there's many different variables here. Show you what the data set actually looks like. That's the code book. So you can look up what this data is about. Show you what the actual data set looks like. I'm going to open it up in SPSS. You have an Excel version of it. You have an Excel SPSS version. You got two versions actually. One is the full data set. I'm using 2013 here. So I think the most recent one that's available is probably like 2015, but I'm using 2013 here. If you want to download a more recent version of it, you're welcome to do that. Okay, so I'm going to open data, and let me find it on the desktop. Okay, and here's the full set. Okay, and it's a full set right here. Okay, now notice these are all, see all these different variables that are here? Just keeps going and going and going. Some of them are obvious: recreation, stairs, mood, there's mood, so on and so forth. There's all sorts of data that's being collected, a lot of it categorical variables. Now, if I go to the variable view, you may notice that the values are not filled in, right? It doesn't say one is good mood, but one is like depressed. It doesn't say that. Where do you get that information? You have to get it from the code book, where it says one represents this, two represents this, three represents this. Now, but there's a lot of variables. So now, obviously it would be crazy for me to sit here and do 180 variables, like code them and stuff like that. So what we've done is, oops, I'm going to close that. No, open. What we've done is, oops, I don't know why it closed. I only closed that one file. Come on, back up. Okay. It's fighting me. Here we go. Okay. Open. Data. Here's a simplified version of it, which has all of the other variables taken away, and only those flu variables, the ones I chose, are still there. Should open in a second. Let's try this again. Open. Data. Version. Processor ready. So where's the window? Where'd it go? Some reason it's fighting me. Yeah, there's a file there. Let me quit SPSS and reopen it. Yeah. Oops. Open. Okay, there we go. So you see this one only has the variables that were in that list, maybe one or two extra as well. So you're not dealing with all of those different variables. Let me see if I was generous. Did I not code this? Oh no, it's coded. You can see here, you can see it's labeled. Actually, no, the values are not coded. I might go in there and code them for you. I think the last time I did this, I wasn't that generous. So I made you guys code them yourself, the ones and twos and stuff like that. But I might go in there and code them for you so that when you change up here to view and you turn the value labels on and off, you can actually see male and female or yes and no and so on and so forth. Insured yes and no, type of insurance under insurance 5 and so on. So in the meantime, if you want, you have the code book there. If you want to get a head start, you can do the coding on this yourselves or look through all the code book and look at all those variables and decide which ones that you want to work with. Okay, so that's what this stuff looks like. And then you'll just wind up doing the statistical tests that we've been doing all along, both the descriptive statistics and some individual tests. So let's take a look at I mentioned categorical variables. Oh, by the way, I wanted to show you something interesting. I don't know how many of you guys got a chance to look at this. Remember we did a thing at the beginning of the semester where I had like a population, a bunch of numbers on a grid, and I asked you to randomly choose people from that population. And we talked about all the different ways that someone might generate random numbers, right? It's not that easy because how do you tell a machine that has to follow instructions to do something random, right? So it isn't that easy. There's always a little bit of an issue. This is a major network company that provides security for networks, and this is the way that they. We wanted to show you how we created our amazing new website with Wix. Now we know that having a great website is an ad. This is the way that they manage to create random numbers.
Computers aren't very good at picking random numbers. Every part of a computer is designed to predict.
See what he's got behind him there?
Logical patterns. You put the same numbers in,
lava lamps.
you're going to get the same
they have sensors behind the lava lamps, tracking the lava lamps all the time, generating zeros and ones. And that's how they, when the bubble goes by and stuff like that, that's how they generate those numbers.
Which is
why they have like 1,000 lava lamps running continuously,
Cloudflare
constantly
is a service
generating
that
random
protects
numbers.
websites and web services and sort of sits in front of them as a gatekeeper. Somewhere around 10% of the web flows through Cloudflare.
10% of the web goes through this site, and this is what they're using to generate random codes, random numbers, for passwords and for protection.
In short, these folks deal with a lot of encrypted internet traffic, so they need a lot of random numbers. It is possible to write code that will simulate randomness, and that's good enough for a lot of users, but in theory, those numbers could be predicted. They're just being generated by code.
Right. So basically saying, I don't know if you can see this stuff on the bottom. I don't want to hook up the speaker and stuff like that. But basically he's saying that, like, if you have a computer, somebody can deduce how it's being done eventually and replicate it.
On a phone, maybe even the accelerometer or other sensors. In all those cases, they generally discard the bigger parts.
So at any rate, you can take that video. The link to that video is online. You can listen to what he's saying. Okay, so let's talk about this other way of dealing with data, categorical data. Okay, which we have an issue. We really haven't dealt with that very much, and how we might handle it. Then we'll go back and we'll do a review of the other material that we're interested in. The stuff is coming on test. And again, like I said, we're going to review it again on Thursday. And we're going to review it again. Well, Thursday I'm going to split it because there's other people like a lot of times tune into the review. So Thursday will probably be a combination of hypothesis testing and some chi-square. But then on Sunday I'm going to concentrate on just what you need for the test. Okay? Or Saturday. I'll try and do it on Saturday. gives you an extra day to listen to it. So let me just get on Blackboard now, which is kind of a pain in the butt. They, you know, they don't let you bookmark the link to Blackboard for some reason. So it's kind of hard to get logged on. Fortunately, it hasn't logged me off, so I'm still on there. Okay, I just want to get into this week. All right, save that up there. Okay, I'm gonna kind of do this off the cuff because I think I'll be able to do it a lot quicker. Okay, so now let's say you were running an emergency room, and in your emergency room, you notice that you get these days with all these bike paths and everything else, and the traffic is ridiculous. You're getting a lot of people coming in there with traumas associated with coming off a bicycle, right? And you notice that, gee, you know, some of these people that come in were wearing a helmet, or they were not wearing a helmet, right? And some of these people had head injuries, or some of them didn't have head injuries, no head injuries, right? Well, those are two variables, aren't they? Was the person wearing a helmet or not wearing a helmet? Helmet status, let's say. Did they have a head injury or did they not have a head injury, right? So you have two categorical variables. Each categorical variables has, in this case, happens to have two possible outcomes: head injury or no head injury. Okay, so let's draw a table, a contingency table, we'll call it. Okay, and this table is a 2x2 table. Okay, and it's going to look something like this. And in the rows, we're going to put the exposures, right? No helmet or helmet. And in the columns, we're going to put the outcome or the disease: head injury or no head injury, right? So now I'm going to examine. It turns out that we have a total of, over the course of a week in the emergency room, we get 200 people coming in. It's a very busy emergency room. We get 200 people coming in that experience head injury, that experience injuries as a result of bicycling. Okay, and it turns out when we survey this, that we find that out of those 200 people, I'm arbitrarily going to make it 100 and 100. Right? We know that it'll never really come out exactly the same number. But let's say 100 of them were not wearing a helmet, and 100 of them were wearing a helmet. Right? Well, then I'm going to examine those 100 people that said they were not wearing a helmet. How many of them had a head injury when they came in here? And let's say it turns out that 30 of them had a head injury, 70 of them didn't have a head injury. Well, how about people that were wearing a helmet? What was that like? I mean, you wear a helmet, you still can get a head injury, right? So, but maybe I found out that 15 had a head injury and 85 didn't have a head injury, right? Out of those 100 people that were not wearing helmets. Well, that's pretty interesting, right? First of all, number one, what would I expect if helmets didn't help protect head injuries? I would expect the same amount of people that had the same rate of head injuries in people that wore no helmet as wore helmets, right? I'd expect the same rate. Here it looks like out of 100 people, 15 that were wearing helmet had head injuries, and 30 of them didn't have head injuries. Well, let's take a look. Let's predict what's the risk of falling off your bike and having a head injury if you're not wearing a helmet or if you are wearing a helmet. So that seems pretty easy, right? 30 out of 100 that were wearing no helmet had a head injury. That's 30%. What percentage had wearing a helmet had a head injury? 15 out of 100. That's 15%. Okay, so another way for me to state this is to say the risk of having a head injury if you bicycle without a head injury helmet is 30%. The risk if you are wearing a helmet is 15, right? So this is the risk given each one of these different exposures. You want to know something? I'm going to set up a ratio. I'm going to call this the risk ratio. Okay. Well, the risk ratio is one thing divided by another. I'm going to say, let's compare the rates, the rate of risk for no helmet versus helmets. And I'm going to say, well, the risk ratio is going to be equal to 0.30 over 0.15, and that's equal to 2. What does that tell me? That tells me that I'm twice as likely to have a head injury if I don't wear a helmet, right? That's the impact of not wearing a helmet. Okay, so now the problem I have is that, if I did this and I did it with left-handers and right-handers, right? And 100 and 100, what would you expect there? I don't think it makes any difference if you're left-handed or right-handed if you get a head injury, right? So I would expect to get the same percentages, maybe 25% and 25%. But what's the odds of that happening? Getting exactly that proportion, getting exactly 25 and 75 and 25 and 75. Pretty small, right? Maybe I'll wind up getting 22 and 88. Maybe I'll want 78. And this one maybe 26 and 74, right? Not exactly, I wouldn't expect it to be exactly the same rate, just cause a chance, right? So now, how far apart do these have to be from being the same rate for me to say that they're really different? In other words, our null hypothesis here is that there's no association between wearing a helmet and getting a head injury. Our alternative hypothesis is that there is an association, right? So what's my job here? My job here is to prove with less than 5% chance of being wrong that this difference is not due to chance. Wow, that's quite a thing I have to prove there, right? Because how do I know that 30 and 15? Why maybe this one it was really 20 and it read a little low, and this one was really 20 and it read a little high. It just happened on that day. We happened to get a lot of people with head injuries that weren't wearing helmets. How do I know that this difference is not coincidence or random chance? Okay, well, that's our job here. One way to measure this is risk ratio. There's another thing that we use called odds ratio, kind of calculated in a similar way. Okay, but before I get into those two, let's take a look at that table again. Okay, this is no helmet. This is helmet. This is injury. And this is no injury. Okay, and I said 30 and 15 and 70 and 85. Okay, so now I'm going to change this number a bit. I'm going to change this to 20 and 80 because it's going to make the math work out a little bit easier. Okay, so now that's out of 200 people. Okay, well, out of this whole pot, if I ignore whether the person was wearing a helmet or not wearing a helmet, what was the prevalence of head injury in this population? Well, how many people had a head injury? 50. And 150 didn't have a head injury. So what's the prevalence in this population of head injury? 50 out of 200, it's 25%, right? I'm going to make another table here. Okay, in this table, I'm going to put in here, again, this is injury, no injury, this is no helmet, this is helmet. In here, I'm going to put in what I would have expected to happen if there's no association between wearing a helmet and having a head injury, right? So we have, say we have 100 people as we did up here, and 100 people here. What would I have expected to happen? The prevalence for the whole group is 25%. Well, I would have expected to get 25 out of 100 having head injuries and 75 not. What about people with helmets? Same thing. Out of 100, I would expect 25 and 75 to not have head injuries, right? I'm going to name these two tables. I'm going to call this one my observed values, and I'm going to call this one my expected values. Okay, pretty simple so far, right? Okay, so now I'm going to say to myself, you know, how different are the numbers in my observed values than my expected values? If there's a small difference, that's probably just due to chance. But if there's a big difference, there's less and less. The bigger the differences between these boxes on top and on the bottom, the less likely that the difference is due to chance. So how am I going to calculate that? Well, I'm going to make up a new statistic. I'm going to call it chi-square. Chi-square, right? Chi is like a capital X in Greek, as a Greek letter. So chi-square, I'm going to say that chi-square is equal to the difference between the observed value and the expected value. Now, I expect that if there's no association, I expect that to be a small number, right? So I'm going to say 30 minus 25, or observed minus expected. The only problem is, you know what's going to happen here, just like we had problem we had before? That's going to be a negative 5. And then when I go with this 20 minus 25, that's going to be a positive 5. 20 minus 25 is going to be a negative 5. So I'm going to wind up canceling out if I just add them all up. So just like before, in order to get rid of the signs, I'm going to square them. Right? Observed minus expected values squared. But now, because I've taken that number and squared the difference, I'm going to get rid of this squared difference by dividing it by the expected value again. So it really brings it back down into the range of where these numbers really are. And I'm going to do this not just for this box and this box, but I'm also going to do it for each one of these other boxes. So I'm going to do it 4 times. Squared over expected plus observed minus expected over expected. I'm going to do it 4 times for each one of these 4 boxes. Matter of fact, let me do it right now. Chi-square is equal to, let's start with this first box, upper left-hand corner. 30 minus 5 is 5. Squared is 25. 25 divided by the expected value, which was 25, is 0.2. Right? Am I right about? No, I'm not. I'm wrong. Wait a second. Let me do that again. 25 squared divided by 20 is 1. Don't let me get away with that stuff. Right? Is 1. Then I'm going to go to the upper right-hand box. 70 minus 75 is negative 5. Right? Squared is 25 plus 25 divided by 75 is 0.33. 25 divided by 75 is 0.33.
Why is the 75 your expected value?
That's your expected. 75 is your expected value because the prevalence was 25%. So if you have 100 people that weren't wearing a helmet, you'd expect 25 of them to have head injury and 75 of them not to have a head injury. And the same thing on the bottom. If this were 200, then you would expect 50 in here and 150 in here, right? That's just what we would expect if there's no association. We'd expect them to all have head injuries at the rate of the entire population.
Professor, the third column, is
Yes.
that O minus N or?
That's observed minus expected over expected. These are all the same.
Oh, it's all the same.
They're all the same. Observed minus expected over expected. I'm going to do it for the bottom left-hand corner. 20 minus 25 is negative 5. Squared is 25. Divided by the expected, which is 25, is 1. Plus, the last one is going to be 80 minus 5 is 5 squared is 25 divided by 75 is 0.33. So if I add all of these up, my chi-square value is equal to 2.66. Right?
Why did you go back and forth?
I'm sorry.
Why did you go from
I could have done it in any order I wanted. Just I have to do it for all 4 boxes. Right? I have to do observed from the value in the upper left-hand corner for observed versus the value for the expected value in the upper right-hand corner of that table. In other words, I have to do it for these boxes, right, and these boxes. Right? Observed and minus expected. I'm comparing them, right? So you can see that this number that I wind up with, if the differences are big, you're squaring them and dividing by expected value, this number is going to become big, right? So now how much is big enough for me to reject the null hypothesis? To say that there is an association between wearing a helmet and having an injury. How big does that number have to be? Well, we need a table to tell us that, like the t-table tells us the probabilities. There is a chi-square table. I'm going to carry this over. Chi-square is equal to 2.66. Okay, so now you can imagine that, we could do this. What if we were doing this by ethnicity? Like this is one ethnicity, this is another ethnicity. You could have 10 rows and 2 columns, or you could have 10 rows and 3 columns, right? Could be a lot more numbers that you're adding and subtracting and squaring and so on and so forth. So that would affect the size of the number also. So as you can imagine, there is a degrees of freedom involved here that you have to, when you go to the chi-square table, you have to account for. We'll go to it shortly. Okay, so the degrees of freedom for any of these analysis is going to be equal to the rows minus 1 times the columns minus 1. So how many rows did we have here? 2. It's 1 times columns 2, 1. So 1 degree of freedom. That's what we have here. Right? So I have 1 degree of freedom, and I want to know how big my chi-square has to be for me to reject my null hypothesis and be 95% certain that I'm not wrong. In other words, have less than a 5% chance of being wrong. What's the chi-square distribution look like? Chi-square distribution looks like this. It's not very likely, this is probability, not very likely that you're going to get a 0. They're going to be exactly the same numbers, right? So that's the low probability. Pretty higher probability that there'll be a small difference. But then as the difference gets bigger and bigger, the probability gets smaller and smaller that you would get that big a chi-square when there's no association. So we want to make sure that our chi-square could be 1, 2, 3, 4. We want to make sure that our chi-square is so far out, that chi-square number is so far out that this area is less than, what do you think? 5%, right? There you go. You guys know more about statistics than I do at this stage. You want to make sure that that's smaller than 5% chance of this number happening for chi-square when it could have been no association, right? So let's go find a chi-square table, see what it looks like. Okay, I should have it pretty available here. And here's a chi-square table. So how many degrees of freedom that we have? 1 degree of freedom. So what is the probability of exceeding the critical value when there's no association? So we want it to be less than 5%. So our chi-square has to be 3.841 or larger. That's our critical value for chi-square. Okay, if I want to be 99% sure, an alpha of 1%, our chi-square has to be 6.635. This is lit up in green because obviously that's the one that you're going to use the most, right? Now, if you have other degrees of freedom, more columns and rows, that makes your critical value chi-square bigger. So we need to exceed the critical value of 3.84. Okay, did we do that in this case? No. So what happens? We fail to reject. Okay, now had I done this, whoops, let's go back a page. Had I done this, let's say if I had said 40 and 60, right? And 20, it's still 20, 40, it's still Oh, this would be different. This would be 60. So the prevalence would be 30. So this would be 30 at 100. Had I done it this way, there would have been if there had been a bigger difference, 40 and 20 instead of whatever it was before, 30 and 20, 30 and 20. Had there been a bigger difference, then this number would have been bigger, and the whole number would have been bigger, and my chi-square would have been calculated, and maybe my chi-square would come out to be 4.1. In that case, I would reject my whole null hypothesis and say that the difference between my observed values and my expected values is large enough that I can say with less than 5% chance of being wrong that there is an association. Reject the null hypothesis that there's no association, accept the alternative that there is an association between wearing a helmet and getting not wearing a helmet and getting a head injury. Now, I started to tell you that there's another way that we can also calculate this, and that is we already got the first one, right? We already got the first idea that I said 30 and 70 and 20 and 80, and this was 30%. This was relative risk or risk ratio. Sometimes you use the term relative risk. The risk rather was 30%, and down here, this is a new example. Down here, the risk is 20%. So the relative risk is 30.30 over 0.20 is 1.5. So the relative risk is 1.5 times. 1.5 times is likely to have a head injury if you don't wear a helmet, right? In this study. Okay, so now the problem is again, this could just be due to chance, right? So in order to prove that this relative risk, if there's no association between wearing a helmet and not wearing a helmet, what would you expect the relative risk to be? 1. You'd expect we get 30 out of both or 20 out of both, and we would expect the relative risk is equal to 1. So our null hypothesis is that the relative risk is equal to 1. And our alternative hypothesis is that the relative risk does not equal 1. So how do we demonstrate whether it does or not, right? We want to prove that it's not equal to 1. So what we do is we create a confidence interval for the relative risk based on this information. Now, I'm not going to ask you to do this manually, right? It's really kind of doing work with two proportions. I'm not going to ask you to do it manually. We use SPSS to do it. And if SPSS tells you that in this case, the relative risk is 1.1 and the 95% confidence interval is 0.9 to 1.6, would you reject your null hypothesis? No, you wouldn't, because it could be less than 1, right? It could be 1. 1's in there. It could be 1. But if I told you if SPSS told you your 95% confidence interval was between 1.2 and 1.6, well, then you're 95% sure that your relative risk is not, your true relative risk for the entire population is not equal to 1 because it's outside of the confidence interval. So you would reject your null hypothesis and accept your alternative hypothesis. Now, relative risk is such an easy thing to understand that a lot of statisticians were disturbed by that, so they invented something called the odds ratio to confuse you, okay? I mean, it really is really easy. Isn't it really easy to understand, kind of? Now, the odds ratio is calculated a different way. Okay, so now here is no helmet, helmet. And this is head injury and no injury. Okay, so I'm going to take these same numbers, 30 and 20 and 70 and 80. Okay, so the odds work a different way. If you go to the racetrack and they tell you, well, this horse pays 3 to 1. The way that those odds are calculated is that for every dollar you bet, you get $3 if the horse wins, right? Because 3 to 1, 7 to 1, less likely a horse is going to win. You get, for every dollar you bet, you get $7 back. The reason why they do that is because it's easy to calculate the payoff. What it really means is those odds ratio is if this race were run 4 times, this horse would lose 3 times, win once. That's the prediction. So when you talk about risk, its risk of winning is 25%, 1 in 4, but its odds are 3 to 1. Get it? There's a difference. So we can do the same thing here. What are the odds of having a head injury if you don't wear a helmet? Well, it's equal to 30 over 70. Not 30 over 100, 30 over 70. And what are the odds of having a head injury if you don't wear a helmet? Well, that's equal to 20 over 80, right? Out of every, out of every 100 times that you had injury, 20 times you get injured, 80 times you win. Okay, so what does that come out to? Well, let's see. I wish I had made them easier numbers, but we'll have to deal with this. 0.3 divided by 0.7. This is, I just rounded it off. That's 43%. 0.43 is the odds. And let me clear that. And the odds, if you didn't wear a helmet, were 20 over 80 is equal to 0.25, right? So our odds ratio, which again, your expectation, if there's no association, your expectation is the odds ratio would be equal to 1. So our odds ratio is equal to 0.43 over 0.25. Eek, where'd it go? 0.43 divided by 0.25. Oops. 0.43 divided by 0.25, which is equal to, oops, that's not right. Let me make sure everything's cleared out here. 0.43 divided by 0.25, 1.7. Okay, I'll round it up to 1.7. 1.7. Okay, so again, SPSS will calculate a confidence interval for that 1.7. And if a confidence interval comes out to be 0.5 to 2.0, well, our expected value for the odds ratio, if there's no association, is 1. So 1 is within our confidence interval. It could be 1, but if our confidence interval for 1.7 turns out to be 1.5 to 1.9, well, then 1 is outside of our confidence interval, so we reject our null hypothesis. Again, I won't be asking you to calculate odds ratio, confidence intervals for the odds ratio. I might ask you to give you this information, ask you to calculate the relative risk, or ask you to calculate the odds ratio, because it's an easy calculation. But as far as the actual confidence interval for either one of those, we'll leave it to SPSS. Yes.
Just a quick question for the top grid for the relative risk. You had 0.30 over 0.25.
Yes.
I didn't know where you got the 0.25.
Oh, did I say that? 0.20.
Okay.
0.2. Yeah, it's 1.5.
Okay.
30 over 20 is 1.5. Just I'm not even sure how I wrote it. So yeah. So that's what we're dealing with here. And why is this important? Because when you go back and you analyze, gee, did you have health insurance? Did you get a flu vaccine? Right? What do you have? You have categorical variables. You have people that have no insurance or have insurance, and you have people that got a vaccine and no vaccine, right? Now your numbers are going to be enormous, right? This might be 3,000, and this might be 5,000, and for no insurance, so this might be 6,000, and 1,500 or something like that for people that had health insurance. So you're going to be dealing with big numbers, but because you're dealing with categorical variables, you need tools to do the analysis. So you got 3 tools now. You got chi-square, right? You have relative risk, right? Not equal to 1, so that's what you're trying to show. And chi-square is greater than the critical value, right, of chi-square. You want odds ratio is not equal to 1. Right? So you want to show that. What do you think it means if I have an exposure here, like for instance, I'm going to be comparing heart disease Heart disease, yes. Heart disease, no. Right? And the exposure I have here is, let's see, eat a lot of bran, right? And eat no bran, right? And it turns out that people that eat bran have a lower rate of heart disease, and the odds ratio comes up being 0.75. What does that tell you? If the odds ratio is less than 1, it tells you that the exposure is protective. It lowers your risk. Your risk is only 75%. It would be people that don't eat oat bran. But if the odds ratio, like for the helmets, if your odds ratio is greater than 1, that tells you that that exposure increases your risk. Okay? All right. So I think that's enough of that. And we can, let's take a break and we'll go back to our review of stuff that might be on the test. I got to take a quick run out there before. So you guys in the meantime, relax. I'll be right back. I promise. I'm leaving my equipment here. I have to put my other stuff, so you know I'm coming back. Yeah, test, right? Chi-square. Not complicated, right? Everybody's comfortable with this? Not really. Okay. Just saying that.
Yeah. Yeah, it'll make everything more yeah.
Do you know, okay, for assessing, like in community nutrition, you know where this data, like how to access this data set?
Yeah, the one with the community,
That like the guy presented on. Yeah. So
is there something particular in your
like childhood obesity. Yeah.
So, go down to yeah.
That's not a good picture.
Oh, sorry. So then, yeah. Yeah.
No. But I typed in childhood obesity.
Maybe not that one. Maybe it's too.
But he showed.
Yeah. This is the one with like massive. Yeah.
Okay, one was. Okay, so this one came out to 1 plus 23.
Wait. I could put
Slash. Slash.
real.
Okay, so 1 plus 23 plus 1. Plus 3. Okay, that's one.
I go to the library. Just talk to the
Yeah.
person.
Oh, yeah. Yeah.
Water.
I
I know. Yeah.
And then I really, you know, she might forget.
So, fizzling out, like, is that possible?
I'd rather present conditions.
I'd like to cover for my keyboard though too. So can you?
Yeah, yeah.
Which is good. No, you guys, I said I shouldn't have to go ahead and do it to 2019.
Of course.
I'm not gonna say, of course, I don't trust them. They might say, you're supposed to do it now.
But I don't wanna take it out.
Yeah, but why would I pay for all that? Yeah, and I'm not starting until.
And make sure community file pages. Yeah. We like doing. I mean,
Right,
some
so
of the
worksheets.
worksheets.
35 and 25 is
We already make a lot of.
5. 5 times 5.
Yeah.